Hello, everyone, and welcome back. In the previous few videos, we've been talking about functions, and in particular, continuous functions. Now, we had a lot to say about continuous functions. We have important theorems, such as the extreme value theorem and the intermediate value theorem. And then we zoomed down a little bit and talked about vector spaces and Banach spaces. And what we're going to do now is start talking about our typical calculus questions associated with functions, and that is derivatives and integrals. Now, if you think about the usual sequencing of a calculus course, you typically learn derivatives first and then maybe integrals afterwards. And you learn through the fundamental theorem of calculus that these two things are intimately related. Now, what we're going to do in this class is flip that on its head. We're actually going to start with the integral and eventually make our way to the derivative after a few more lectures. So with that being said, in this lecture, we're going to introduce the basics of what an integral actually is. So let's go ahead, let's jump right in. Now, you probably remember from your calculus class that an integral is abstractly capturing the area underneath a curve, right? So maybe we have some kind of function, say f of x, and we are looking between, say, a and b, and we would say that this area in here is equal to the integral from a to b of f of x dx, right? This is what you learn in your usual calculus class. You augment this to say if the function goes above and below 0, you get a signed area. So that is, you assign a positive value to the area above the x-axis, and you assign a negative value to the area below the x-axis. But nonetheless, you're still doing this sort of area computation. But we should interrogate this for a moment. What is it that this actually means, this integral notation? Well, we remember that this comes from a Riemann sum. It comes from putting little rectangles underneath our function and letting the width of these things go to 0 and asking ourselves, what is the limit? And if you did this in a calculus class, it's done in a very, very informal way. We sort of skirt around a lot of the details. And that's the goal here, is to reinterrogate these details and understand precisely what we mean by letting these limits go to 0. Now, remember, we've talked a lot about limits. So now things should be able to be described in a perfectly precise manner. And so we're going to begin with a definition of what's called a partition. So let's say a partition, so we'll put this in red to emphasize it as usual. So a partition, which we will call P, is an ordered list of finitely many points, starting with A, and ending with B. So these are included in your listing, with, of course, B being bigger than A. So thus, we can write P equal to, say, x0, x1, x2, all the way up to xn. It's an ordered list where A is your first point, and then your next point is above it, and then your next point is above that, and so on and so forth, until you get all the way to the right-hand side. Now, we can go further on this. We can say these points, PTS as points, are regarded as partitioning the interval A to B. So again, if we go back up and take a look at our integration here that's taking place, that is the interval a to b that we are looking to partition. If you remember what a Riemann sum does, it discretizes the interval. That's what we're essentially doing here. So this discretizes it into n contiguous subintervals, which are xi minus 1 to xi. So the previous element to the current element, and that goes from all I from 1 to n. And the length of the ith subinterval is given by, well, we call this delta xi, which is just the distance from xi to xi minus 1. Now, there is nothing in this definition that says that all of the delta xi's have to be the same. This is probably what you did in calculus. You usually use a regular stepping to partition up your interval. But for us, we're going to do things in complete generality. There's nothing that says that everything has to be equally spaced here. Now, let's keep going. What we'll call the mesh. So the mesh of the partition is denoted and defined by, well, here's our norm notation. So the two lines, and P, that's of our partition. This is going to be the maximum of the delta xi's, so the length of these subintervals. So you ask yourself, what is the longest subinterval that is in my partition? Then I'm going to call this the mesh of my interval. And let's keep going because there's more to go along here. In each subinterval, we select an arbitrary, now this will be in red again, evaluation point which we're going to denote by xi bar, and it belongs to the interval xi minus 1 to xi. And finally, we can define a Riemann sum, right? So this is a huge, huge, long definition here, a lot of moving parts, but this allows us to define, so we define the Riemann sum and let's take a look at it. Well, this is, so PF given the evaluation points. So all of your information is there. F is your function. You have your set of evaluation points. P is your mesh. So this is just one big piece that tells you this is a Riemann sum. This is equal to, well, it's the sum of those rectangles underneath, where the height of your rectangle is given by F at the evaluation point, and the width of your rectangle is given by the length of those subintervals. Now, if you think back to a calculus class, you typically use maybe a left Riemann sum. That means your evaluation points were the left endpoint of each of those subintervals. Or maybe you used a right Riemann sum, where the evaluation point is the right endpoint of the subinterval. Sometimes you even use a midpoint rule, so the middle of the subinterval. But the point with this definition is not only that the subintervals can be different lengths, but also you can evaluate at any point inside of them. We don't have to have a rule. It doesn't have to be regular like it might have been presented to us in a calculus class before this. Okay, so this is a way of approximating the area underneath these functions based on these rectangles that I showed you. Now the question is, how do we move to this notation of our usual integral, right? That sort of a big S looking thing here. Well, we've got one more definition that we've got to go through. So it's going to be a long one again. So bear with me. There's a lot of maybe new terminology that we need to work with here. But we're going to say that the Riemann integral, so remember we had the Riemann sum, now we have the Riemann integral on a closed finite interval. So we are always going to be looking at finite intervals. We're not going to talk about improper integrals in this class. So it's something like 0 to infinity. It's always going to be from 1 to 2 or 0 to 3, finite intervals. So a to b in our case of a real valued function let's say f. This is said to exist and have value L. L and R, provided that for each epsilon greater than 0, so here it is, here's our real analysis portion of this, so that for each epsilon bigger than 0, while there exists a delta greater than 0, such that if we take a mesh of our partition smaller than delta, so this means the maximal subinterval, its length is smaller than our delta value. Remember, there's a lot of new definitions that are built into this, so be careful. Well, this implies that the Riemann sum is within epsilon of its limit. So this is a very, very new form of convergence. And we also need to put this in. This is independent. Let's underline that just to emphasize it, of the choice of partition. And evaluation points. Okay, so this is very, very important here, right? This tells us that it doesn't matter how you pick your partition, as long as that partition has mesh smaller than delta, then you are within epsilon of the limit of this thing. So that is a very, very key component to this, right? So if you think about how you do this in maybe a calculus class, you say, well, let delta x go to 0, and I can kind of see what's happening here. But typically when you do that in a calculus class, you have prescribed your evaluation points, your subintervals, your mesh, all of those pieces. Now, what we're saying for this is that actually you should be able to do it independently of how you choose your partition. Doesn't matter how I discretize a domain. Doesn't matter where I evaluate at. As long as I take points close enough together, I can get very, very close to what the limit of this thing should be. And let's keep this going a little bit, just a little bit of notation. So in this case, we write, you know the notation here. So in this case, we write that the integral from a to b of f of x dx is equal to L, the limit. And we also write, so since this thing, so we write also, we have a limit now, so we can say this is the limit as the mesh goes to 0 of these Riemann sums. And again, this is independent of the actual mesh that's chosen and the evaluation points. So this is tough. This takes a little bit of work to get your head around. I totally recommend, pausing for a moment and really trying to work through this. Okay, now the last piece of this, I want to put one more piece at the end of this definition. So the family of all so-called, now we have another definition, Riemann integrable functions. So functions that have a Riemann integral, or a Riemann integral functions, f is denoted by R of AB. Okay, so the R stands for Riemann. The AB tells us that it's on the interval A to B. And this is very similar notation to what we saw with the continuous functions, where C stood for continuous. So what this is really saying is that if I say a function belongs to R of AB, well, this is if and only if, well, this thing exists. And we understand this shorthand notation in terms of the limit that is above, in terms of these partitions and these meshes and all of this sort of very complex machinery that's at work here. Okay, so we've learned a lot of definitions here, but let's actually do some examples to see if we can compute the integral using these definitions. And let's start with a really easy one. So let's ask ourselves, what is the Riemann integral of a constant function? Now, you probably, or you should know this, right? Because this actually just forms a perfect rectangle. So if you have a constant function at C, it's going to be C times the length of that interval. So we're going to say, let this be a constant. And this is going to be for all x in some interval. Well, then we claim that this f is actually Riemann integrable, and its integral is just equal to C times B minus A. And again, this is just the height C against the width of the rectangle, or the length of the interval B minus A. And to see this, we can let P be any partition of AB. It doesn't matter what it is, but let's just take a look at this. Well, then the Riemann sum is, well, the Riemann sum here is going to be completely independent of P. So let's see why. Well, the evaluation points don't matter because I'm always just turning up the same value inside my function, right? I'm always getting f of xi. So that would be what would be in here, xi bar, delta xi bar. But f is always returning the same number, c of delta xi, which gives me, I can pull this c outside here, and I get this little summation, and I can unpack my xi's, or my delta xi's, so that this becomes xi minus 1. This is a telescoping series. You're left with just the beginning, x0, and the end, xn. But we remember, if we go back, that xn is b, x0 is a. So this leaves me with c times b minus a. And so therefore, every single Riemann sum always gives me c times b minus a. And therefore, I take the limit of the mesh going to 0. It doesn't matter because this thing is independent of the partition. So this was a relatively simple one to check. Now, you might have a question You might say, is every function Riemann integrable? And the answer to that is no. There are many, 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 many functions that are not Riemann integrable. Now, the functions that you know and love, like the polynomials or rational functions, these things are all Riemann integrable as long as they're defined for their whole domain. But let me show you a function that you probably haven't thought about before. This is going to be a very complex looking function. In fact, we are not able to draw it. So it's going to be 1 if you feed in a rational number between 0 and 1. Whereas it's going to be 0 if you feed in an irrational number between 0 and 1. Okay, so you can't draw this because we can't draw, or we wouldn't be able to indicate or distinguish between the rationals and irrationals between 0 and 1, because we've already seen the rationals are dense. So they sort of fill up that whole interval. So we claim that f is not Riemann integrable. This thing does not have a Riemann integral. So how do we see this? Well, let's let P be any partition. Doesn't matter how big or small this mesh is, no matter what. But every subinterval contains a rational number due to the density of these rational numbers. And it also contains an irrational number. So we are free to choose, say, xi bar in Q for all I equal to 1 to n. And this will give me, since I'm using evaluation points that are all rational, then my Riemann sum will become just a constant function. All you're going to see is the value 1 because you're always feeding it rational numbers. And so you will get, just like before in the previous example, I get 1 times delta xi, which is just equal to the length of the interval times 1. So that's going to be 1 minus 0, which is just equal to 1. So in this case, if you're using rational evaluation points, so for example, if you're doing this on the computer where you only have access to rationals, then your Riemann sum is going to return 1. But if my evaluation points are all chosen to not be rational numbers, then this tells me that my Riemann sum is going to be, well, it's going to be the Riemann sum of a constant function again, but now it's the constant function 0. Because I'm choosing irrational numbers, all I can see are this function returning 0. And so therefore, my Riemann sum is equal to 0, no matter how big or small my partition is. But that means that there's no way I can have convergence here, right? We cannot bring both values of the Riemann sums within epsilon of the same number, right? So let's just put a little note here. If 0 is less than epsilon, which is less than or equal to, say, 1/2, which is half of the distance between these two things, we cannot bring these Riemann sums within epsilon of the same number L, which means that this thing does not converge as the size of the partition goes to 0, because we can always, no matter how big or small the partition is, we can always choose the evaluation points, right? We saw that in the previous definition. This definition is independent of your choice of evaluation points. Doesn't matter what you choose, but here we can see that it really does matter. So in fact, we found a function that is not Riemann integrable. Let's take a look at a theorem here. And this one is going to help us characterize some of the functions that are Riemann integrable. And this might seem a little counterintuitive to you, especially if you've done a little bit of calculus before this. So if f is a Riemann integrable function, well, then f is bounded on AB. Now, this might strike you as slightly alarming, right? Because maybe you've seen something like the integral from 0 to 1 of 1 over the square root of x dx. Well, you can do this with usual calculus methods, and you know that this thing is actually finite, that its Riemann integral actually exists. But that thing actually is in shorthand of letting the limit as b goes to 0 from the right. And so we are not considering these types of integrals. We are not taking limits of the endpoints. We are just looking at the actual area underneath the curve over this interval here. And so what this is saying is that if you are going to have a Riemann integral of a function by our definition that we presented at the beginning of this lecture, then your function has to be bounded. So let's take a look at the proof of this thing. So let's suppose the theorem is false. So let f be a Riemann integrable function, and suppose for contradiction that f is not bounded. Okay, so imagine we have an unbounded function that is actually Riemann integrable. So then let's denote L equal to the value of this integral. Remember, this is the definition of being Riemann integrable. So I'm just going to use L again for limit. Okay, again, let's take a look back at this definition here. We can use this epsilon delta notation in order to prove this. So what this really means for this integral to exist, that means that if I choose any epsilon, I can find a delta, so that when I choose a mesh smaller than delta, I am within epsilon of my actual limit. Okay, well then why don't I pick an epsilon? So let's choose epsilon equal to 1. You can choose whatever value of epsilon you want as long as it's finite. I choose 1 because it's a simple number to work with. Well, since I've chosen an epsilon, I know that there exists a delta such that if I take a mesh smaller than delta, this implies that the Riemann sum, regardless of the evaluation points, is within epsilon of its limit. Pardon me, epsilon was equal to 1, which I can actually unpack that inequality right there. So I can say that this is the same as having this right here. So I can slap absolute values around each one of those and distribute over the subtraction here, which tells me that the Riemann sum is bounded above by no more than 1 plus the actual value of the Riemann integral. So we are going to use this bound on the Riemann sum in order to find a contradiction from the fact that we assumed our function is not bounded. Okay, so let us fix a partition P with mesh less than delta. Okay, so that this actually holds. So I said above, as long as I choose a partition that has mesh less than delta, I can get this. Well, okay, let me pick a partition and let me derive a contradiction. So, but if F is unbounded on the interval AB, well, then there exists some subinterval that it is also unbounded on. So there exists an I such that F is also unbounded on xi minus 1 to xi. Okay, right? So if I'm unbounded on the whole interval and I've fragmented up the whole interval into these smaller little components, then one of those smaller components I have to be unbounded on as well, right? Because the unbounded part on the big piece has to be contained, or it has to be represented in one of the small pieces. Okay, so what does this do? Well, this is a problem. This is a serious problem for my Riemann integral now. Because this tells me, or sorry, my Riemann sum, because now my Riemann sum, which I know is no bigger than L plus 1. Well, this thing, let's just look at the definition here. K equal to 1 to n, so I'm using a different index because I is used to denote the interval that I'm interested in, that I'm unbounded on. So just the definition of the Riemann sum so far. Well, I can use the same trick that I used right here, where I distribute over the subtraction. And what I can say now is that this thing is greater than or equal to a huge absolute value. And if I pull out the problem subinterval, the xi, I get the absolute value of f of xi bar delta xi minus, and then the absolute value of the sum of k not equal to I. So every other subinterval of f of xk, pardon me, to xk. So this is using a reverse triangle inequality here. You might have to look this up. So maybe I'll just put a little note. This is since you can do this little trick, alpha plus beta is greater than or equal to the absolute value of alpha minus the absolute value of beta. So that's the little trick that I'm using here. This is called the reverse triangle inequality. I highly recommend trying to prove it on your own to have a little bit of fun. But remember, this thing is independent of the evaluation point, so I can wiggle things around. So let's take a look. F is unbounded on this interval, xi minus 1 to xi, which implies that this thing can be made as big as we want. Why is that an issue? Well, I can choose an evaluation point that will make this whole thing huge. So I don't change any other evaluation points. I keep all the xk bars the same. The only one that I change is xi bar, and I blow up this end here. But then that blows up the value of the Riemann sum, which is impossible because the Riemann sum has a definite upper bound of absolute value of L plus 1. So, but the Riemann sum is less than L plus 1, which means f cannot be unbounded. And that gives us our proof, right? So it's sort of informal how we looked at this. And you can make this rigorous if you need to, but I really want you to sort of see the mechanics of what's happening here. And basically what you do is you identify a subinterval where you have your problem, where you have your unboundedness, and you say, okay, this is not going to work with my Riemann integral because, or my Riemann sum, because that Riemann sum, the height of one of those rectangles can be as big as I want it to. That's essentially what this inequality in the middle of the board is giving us, right? This inequality right here, that's telling us that your Riemann sum is no bigger than the rectangles that you're using to build it. Now, if you can make one of your rectangles as tall as you want it, that means your Riemann sum is going to get pretty darn big. But the issue with that is that we already said your Riemann sum can't get that big because we know it converges. Okay, so that proof was a little bit looser than we're used to, and it's mostly just because it's easier to understand than it is to write down. But let's take a look at a really simple example. Let's say let f of x equal to 1 over x if 0 is less than x, which is less than or equal to 1, and 0 if x is equal to 0. Well, then, from our previous theorem, it's easy to see that this thing is not Riemann integrable since f is unbounded on 0, 1. So this allows us to rule out some functions and tell us that not everything is Riemann integral, even if it's not some ridiculous function like what we saw with this second example here that depended on if you put a rational or irrational number in, right? So there's real cases that are tangible and that are accessible that are not going to be Riemann integrable. And again, I just want to reiterate, this comes from the fact that you're using these rectangles underneath the function in order to converge into the area underneath the curve, or if this thing goes above and below the x-axis, the signed area. Okay, so what we saw in this lecture was an introduction to the Riemann integral. And we saw that there's a lot of heavy machinery and definitions that need to be considered here. And we got to use a few examples to get us a little bit more fluent with these definitions. What we'll do in the next video is we'll come back and we'll continue talking about Riemann integral functions. And in particular, we will show that the space of all Riemann integrable functions, R of AB, is a vector space. So we'll have a collection of 2 vector spaces to talk about now. We have the space of continuous functions, and then we'll have the space of Riemann integrable functions.